Welcome everybody for the first session of the morning of the Current Developments in Mathematics. I'm David Jarrison, one of the organizers, and it's my great pleasure to introduce the first speaker, Santosh Vempala from Georgia Tech. Usually the job of introducing, anyway, Santosh was a colleague of mine and a friend, and I really enjoyed learning from him when he was at MIT, and we're looking forward very much to his talk. I have the challenge in this first lecture of pronouncing the names of in the title here, so I'm going to give you guys a very short lesson in how to pronounce names. The most crucial thing is you need to know the nationality of the people whom you're naming, and then their lettering system, which was translated into Latin letters from some other one. So if you know that these are Hungarians, then it's actually easy because there's a completely phonetic rule for how to pronounce the names. So this is Kanan, well, I guess maybe he's Israeli, but anyway, Kanan Lovas Shimonovich, because the S is a sh sound and the SZ is one letter, and it's the S sound. So again, the Kanan Lovas Shimonovich conjecture. So we're looking forward to more interesting information from Santosh.
Thank you, David. Thanks to the organizers, and yes, it's almost all Hungarians. Kanan is Indian. You were.
Fortunately, phonetic.
Absolutely. Thank you for that. Okay. This is joint work with Untitled from who's currently at the University of Washington. Yeah, he looks just like his picture. So, okay. The talks are about isoperimetry, and I was told that the first talk should be for a general audience, and I might have taken that too literally, so feel free to signal me to go faster. But so what is isoperimetry? You have a function in space or a measure, and you'd like to understand the measure of the boundary relative to the measure of the set itself. The classical question, most classical, what is the set of unit volume in Euclidean space with minimum surface area? And it's the unit volume Euclidean ball. Okay, now to make this a little more general, let's have this parameter, the ratio for a set, for a subset of space or a measurable subset, the measure of the boundary to the measure of the set, and you ask, for example, which 10% subset of a triangle has the minimum internal length or surface area, and suddenly that's not so easy anymore, and so we'd like to study this quantity in general, the isoperimetric ratio or expansion, Siegel constant, which is the minimum over all subsets of measure up to a half, the ratio of the boundary to the measure of the boundary to the measure of the set. Okay, this is the quantity for both talks. And yeah, so why is this interesting beyond the natural question? So maybe another classical question here was, what's the constant for a Gaussian distribution in Rn? And there the answer is nice in two ways. First, it's a precise constant, and second, the subset that achieves this isoperimetric ratio is a half space. In fact, it's a half space for any fixed subset measure. So if you say I want 1/4 of the Gaussian, what's the area minimizing subset? That's again a half space, and so on. Okay, so this is also classical. Now we can ask more generally, when is something like this possibly true more generally? And of course it can't be true in general, complete generality. If you have, even if it's connected and so on, you can have very small partitions between large subsets. What about more structured sets and distributions? So the question is, what is the right generality of distributions and sets to look at this? What structure are we talking about? Certainly not these dumbbell shapes. right? So you don't want to allow dumbbells. So one natural way to not allow dumbbells is convexity, so because you must have the line between every 2 points, and more generally log concave functions, where we make sure that the function doesn't dip on any line. And these are common generalizations of Gaussians and convex sets, so that will be the familiar setting through these two talks. Now for these, half space cuts do not have to be the minimal ones anymore, just as even for the triangle. But you could ask, well, they're not the minimal, what are the minimal ones? And so the conjecture is that for any log concave density in any dimension, half spaces will minimize the Cheeger constant, the isoperimetric ratio, up to a universal constant, independent of the dimension and the measure and so on. Okay, 10. Yes, so P is a measure, so you could take F and then make sure it's integrable and normalize it by that, and you'd get, yeah, that's all. But effectively it is the same. So this was the conjecture in one form. I'll define it in a second form in a second, in a few minutes, equivalently. So the theorem that Kannan-Lovász and Szymowicz proved is the following. Take a convex domain, or Rn, and a log concave function, look at a subset, and they said that the measure of the boundary is at least 2 over the diameter time. Actually, this was earlier. This was by Lovász-Szymowicz and Dyer and Fries. 2 over the diameter times the smaller of the two. And in fact, this is a special case up to that particular constant of isoperimetry in Riemannian manifolds with non-negative curvature or bounds on the curvature. But what Kannan-Lovász and Szymowicz did is they introduced a different normalization. So they said, let's look at the covariance of this distribution. So that's the matrix A. And in particular, its trace. So that gives you the expected square distance of a random point from the center of gravity. And this picture is just showing you that, of course, the square root of the expected square distance can be much smaller than the diameter itself. And their theorem is that the isoperimetric ratio, instead of constant over diameter, can be replaced by constant over this square root of expected square distance. So in particular, if the distribution is isotropic, by which we just mean that the covariance matrix is the identity, so that's a normalization that you can put any distribution with bounded moments in, bounded second moments in, and in that case, this is saying that the isoperimetric ratio is constant over square root n, because that's the square root of the expected square distance, whereas the original theorem, or the more general theorem, would have said constant over n. So, okay. So in these terms, the conjecture can be stated like this. There is a distribution with a covariance matrix. It has this trace. So the theorem said that the isoperimetric ratio is at least 1 over the square root of the trace. And the conjecture is that you don't need the sum of all the eigenvalues in there. You could replace it with just the largest eigenvalue, constant over just the largest eigenvalue, which would mean that what we observe for Gaussians is also true for all log concave functions. This is equivalent to the half space version, because you could look at the projection on any dimension, and then half spaces are the interesting cuts. Okay, so that's the other version of the conjecture. Here's the outline of the both talks. I'll describe why they came up with this conjecture, and connections to probability and geometry, which will take up, and algorithms, and this will take up almost all of the first talk. And then in the second part, we'll see some proofs and techniques, and this will take us to the current state of the art for what the bound is. And the proof turns out to be quite simple at the end, and it's from last year. And I'll mention several open problems and some progress on these. As in the case of the original conjecture, what's going on right now seems to lead to very interesting questions that we don't know the answers to. Okay, so here's the motivation. it's an algorithmic problem. You'd like to sample. You're given a convex body K, and you want to generate a uniform random sample from this. So how is the body given? Well, it's given by what we call a well-guaranteed membership oracle. So for one part of it is that for any point in space, you can say, is the point in the set or not? That's a query, yes or no. And then in addition, some bounds on the domain of, on the range of the set. So there's a little ball contained in the body, and you're given one point in it. So if you don't have a starting point, then you might not get anywhere at all. So you need one point in the set. You're told that there's a little ball inside and a big ball of radius big R containing the set. So some bounds on the set to make it a body. There are related problems we'll see later, computing the volume of such a body and minimizing a convex function over a convex set, which will be quite closely related to the sampling question. Okay, so that's the problem we're working on. And now, how would you sample? So the algorithms are very simple. They're just Markov chains. So at a point x, what you do is you consider a ball of fixed radius delta around the current point. So there's a parameter delta, a Euclidean ball, and pick a random point from that. If that new point is in the set, you go there. Otherwise, you don't do anything. That's the Markov chain. You stay where you are. This is symmetric and therefore approaches the stationary distribution, which is uniform. And the question for an algorithm is how many steps do I need to take, because each step corresponds to a query. Are you in or out, the point I chose? And so that's the rate of convergence, which you can think of as the Cheeger constant of the Markov chain, the state space with this transition operator. And so one thing they proved in a companion paper is that the mixing time of this ball walk from a warm start, okay, that's important. You can't start at corners. You could get stuck right away. In one step, you might have exponentially small in the dimension probability of even making a proper step. But if you start warm, so your distribution is within some bounded distance of the uniform, then in n squared over the Cheeger constant squared number of steps, you will generate a new random point, an essentially independent random point. So one way to think of it, and we'll see this in more detail in the second half of the first talk, is that the Cheeger constant of this Markov chain, or this operator, is directly related to the Cheeger constant of the target stationary distribution, which is a purely geometric quantity. Okay. So this was the motivation. So now if you can prove a better constant, you get a better complexity for the algorithm. So their original value gives you n cubed, because they proved that the psi, the Cheeger constant, is 1 over root n, so you get n cubed. If the conjecture is true, you get n squared. So that's a concrete motivation. So it's the radius of the ball that's used to do this. Now, the point is that you have to choose it carefully. If you choose it very big, of course, you take only one step, but then you might not make a step for forever. So what they showed is that as long as the body contains a unit ball, you can make this delta 1 over square root of the dimension, 1 over square root n. And that's the part of the reason why you end up with the n squared there. I will do that proof, essentially, at least the outline. Okay, so now I move to some of the connections, and these connections were discovered post hoc. The conjecture was made, and then many of these conjectures already existed, but are implied. One of these, which in some sense is one of the drivers of modern asymptotic convex geometry, is the slicing conjecture, which says that if you have a convex body of volume 1, it must have a hyperplane section of volume at least some universal constant. Yeah, so the only normalization is unit volume, and there exists a section of volume at least a constant. An equivalent version formulated by Keith Ball says that for any isotropic log concave density, so the covariance is the identity, if we define this constant, this slicing constant, as the density at the origin to the power 1 over n, or the maximum density to the power 1 over n, those two are going to be within constants for a log concave function, then this is bounded by a universal constant. So your density can't be too high anywhere. This it's a sort of an anti-concentration. So these are equivalent. That's the conjecture. It implies this type of small ball probability result, which says that if you pick a random point from such a log concave density and ask, we know that the expected square distance is n, so you expect it to be about distance square root n from its center. What's the chance that it's only epsilon root n? And this implies that it's epsilon to the power of n. So best possible sort of tail bound, small ball probability bound again. Yes.
So for these three conjectures, some of them feel like they're upper bounds and some of them feel like they're lower bounds. Do you want to comment on
Sure.
the relationships between?
Right. So the KLS conjecture or the Chigger constant conjecture is certainly about a lower bound. This is as stated here. These two are equivalent. Now that takes a proof to show that you can express the.
So the one looks like it's a lower bound on a slice, one looks like an upper bound on the density.
Right. Yes. You're not applying directly to that function. You actually have to take this log concave density defined by the function in a different. Yeah, I could show you the proof, but I think.
You don't have to show me the proof. I'm just trying.
Yeah. No, I understand why you're trying to apply directly to the marginal density. So that's not this function. The function you actually have to apply it to is a lifting of this body to a log concave function. So yes, I won't do that right now. But yes, the one version there looks like a lower bound, and this looks like an upper bound. But actually, the constant c there is exactly this LP. The constant c that you get for this volume of the slice. So maybe it's a good exercise actually, because there's enough in the definitions here to prove that. Now, what's the connection to the KLS conjecture? It actually implies this. Either these are equivalent. It implies this that slicing is true. This was first observed by Keith Ball, and then we also know bounds on this slicing constant that were known prior to the conjecture being made even, and one bound is that it's n to the 1/4, dimension to the 1/4. Bourgain proved n to the 1/4 with a log factor, log n, and Klartag in the early 2000s removed the log using similar proof but more refined. So that's the current bound, conjecture is it's a constant. Okay.
So with this, the concentration.
Yeah.
Quality. So just I can do the calculation, but I can do it in my head. What if we just have a Gaussian? Then what's the concentration on the bed?
Yeah. So this is a type basically. Yeah.
Okay.
Yeah. Exactly. Yeah. Okay. And we'll see that phenomenon again now. So here's another conjecture that predates the KLS conjecture. It says that if you take any isotropic log concave distribution or density, the variance of x, the expectation of x squared is n by the isotropy, nothing to do with log concavity. The variance is order n. Another more transparent way to say it is that if you look at the deviation from root n of the length squared, it's a constant, which means that most of this isotropic log concave distribution lies in a shell, in an annulus of thickness constant, regardless of dimension and distribution. This is sort of as extreme a concentration of measure bound as we get to see. No matter what log concave distribution you have, what dimension you have, most of your distribution is an annulus of thickness constant, while of course the distance from the center, the radius of this is growing with root n. And the KLS conjecture immediately implies thin shell. So that's just an exercise, right? Because you can apply the conjecture just to the subsets induced by balls intersected with the distribution, and it tells you that the boundary measure is at least a constant, right? So, or is at least whatever it is. So you go out distance 1 over that, and you pick up constant fraction of the mass. So within 1 over whatever KLS constant is, you'll pick up a constant fraction of the mass of the distribution, just by applying the isoperimetry repeatedly to a sequence of balls. So you have immediately this quantitative relation that the thin shell thickness is at most 1 over the KLS Cheeger constant. And in particular, if one is a constant, the other is a constant. A bit more surprising, but also proven several years ago, is that the slicing constant is upper bounded by the thin shell constant, and not in a per distribution sense. That might be true, but we don't know it yet. But certainly in the supremum sense, so if you take the maximum possible thin shell constant over all isotropic log concave distributions, that's an upper bound on the slicing constant. Okay, so this is now here is a different implication of the same conjecture. So you have this, most of the distribution is in this thin shell. So now you ask, what happens to marginals? If I take any one dimension and I look at the projection of the distribution on that, well, it's going to be some log concave distribution, projections of log concave or log concave. But in fact, what the thin shell conjecture implies is that random marginals, almost all random marginals, are approximately Gaussian. So not only are they log concave, they're actually close to Gaussian. So formally, or one way to make this precise is that if you have an isotropic convex body K, I look at a direction theta and look at the volume of the slices along theta. So that's just the proportional to the marginal function. Then the probability that this cumulative density deviates from a standard Gaussian by more than delta plus whatever is the Cheeger constant divided by root n is almost 1. It's 1 minus something that's exponentially small in the dimension. So for all but an exponentially small in the dimension fraction of directions, the marginal looks Gaussian up to the Cheeger constant. Okay. In fact, that can be replaced by the thin shell constant there. So that's another implication. You have a central limit theorem like this. Now, there has been much progress on the thin shell bound itself in the past decade. The first interesting bound is that it is in fact a central limit theorem. So you have a ball of radius root n, and you're asking what is the radius here? The trivial bound is that this is square root n, and this is also square root n. As soon as you make this smaller, you get a central limit theorem. And the first bound there is improving it by a factor of square root log n. So already there is something interesting going on. And this was improved over the years, and now it's down to n to the 1/4. We'll see the proof. And therefore, due to this proof, you also get a different proof that the slicing constant is down to n to the 1/4. Now, welcome to interrupt me with questions about this. Another one is the Poincare conjecture, or the Poincare constant, which is essentially the same as the Cheeger constant, but up to a square. So we have smooth functions, isotropic log concave densities, and one way to state the conjecture is that there is a universal constant C, so that if you look at the ratio of the norm of the gradient to the variance of the function itself. So if the function varies a lot, you expect that the gradient should have high norm. That's what's being quantified here. This ratio is at least some constant as a conjecture over log concave densities. So if I define that as zeta p, this is in fact equivalent to the Cheeger constant squared. The first part saying that that it's at least is the Cheeger inequality relating the spectral gap and the Cheeger constant. The other part only holds for log concave functions, and that's due to Boozer and Ledoux. Boozer had a proof that involved a dimension dependence, and Ledoux's proof is there's no dimension dependence. So it's up to universal constant. This is it.
So in that equation, you have for all g something, but then the if takes out.
Yeah. Sorry, I don't need the for all g outside. Yeah. Thank you. I can use the. Okay, so that's equivalent. So now you can ask, here is a different Lipschitz concentration, again taking us back to a classical inequality. So if I have a Lipschitz functions on the sphere in whatever dimension, Levy's classical concentration inequality says that the deviation from the mean or the median is the probability that it deviates by t is something that falls off exponentially in t squared n that I mentioned. Okay. An extension of this or a variation of this to Lipschitz functions, but in Rn and for any log concave density p, not the uniform distribution on the sphere, but any log concave density, says that this deviation is at most not t squared, but t exponential in t times the Cheeger constant. Okay. So this was shown by Gromov and Millman. And you see here that the best thing you can get is e to the minus t, for example, for an exponential density. And so if the KLS conjecture is true, this implies that you would get that. And in fact, it's equivalent. Lipschitz concentration in this sense, exponential minus t, implies the KLS conjecture. So we have this relationship as well. Conjecture implies anti-concentration and concentration. I want to mention one more. It's an information theoretic consequence. So if you have a distribution, you can define its entropy. How many bits do you need to encode its density? And the sort of a classical inequality says that if I take two independent draws from a distribution, and I look at the entropy of their of x plus y over square root 2, it's at least the entropy of one copy. You're taking two draws, you have more randomness. And equality is only for Gaussians, and so in this sense, the Gaussians maximize the entropy. And so you could ask, how far is a distribution from a Gaussian in terms of entropy? And one way to measure this is to see how much the entropy jumps when you take an average like this. So if you look at the different change in the entropy for two copies, the average of two copies versus one, it's related to how far you are from Gaussian, because if you were Gaussian, of course, there's going to be no change. You'll have exactly the same entropy. But if you're not Gaussian, then it depends on how far you're from Gaussian, just measured by the same entropy, times the Cheeger constant square or the Poincare constant. So it shows up again. So to summarize some of the significant connections here, we have the slicing conjecture, the thin shell conjecture, Poincare conjecture, generalized Lipschitz concentration, and the KLS conjecture implies all of these. As we now know, although they didn't know when it was conjectured. Okay, the second part is connections to algorithms. I mentioned sampling, optimization, volume computation, and learning. The general question is, what's the complexity of these computational problems as the dimension grows? Why dimension? It's the number of variables and represents the size of the input in many cases. If not the dimension itself, it's some polynomial in the dimension. So the model, again, to remind you, is that there's if it's a convex set or a set, then there is a membership oracle. It answers yes or no, a starting point in the set, and some bounds on the set itself. If it's a more general function, then you have an oracle that returns the value of the function at any given point. You have some point with a non-trivial function value. We're thinking of this as a non-negative function for now. And bounds on the eigenvalues of the covariance matrix with density proportional to S. So that's similar to these upper and lower bounds on the ball radii containing the body. We're asking for some bounds on this covariance matrix. Towards the end, we'll also see an interesting special case when the convex body is just an explicit polytope. It's given to you as inequalities. Okay, so this is the problem. You have an input function, and you'd like to generate a point which is within distance epsilon, let's say total variation distance epsilon, of the density proportional to S. That's the sampling problem. So you could have, for example, the indicator of a set or some function restricted to a set and so on. Now, I want to mention quickly one example where these sampling problems show up. They are surprisingly practical of late. This is an example from biology, sampling metabolic networks. So these networks to do with how chemicals are changed from one form to another inside an organism like us. So it's modeled as a network with metabolites and reactions, and you'd like to find a mass conserving flow, because there is conservation, which you can express as a linear program. And what the biologists are doing now is to say there are many possible solutions for the metabolism to be doing, depending on various external conditions. Rather than picking one, let's think of this as a convex body and sample over it. Now, the one issue is that the dimension is somewhere between 5,000 for tiny organisms to 100,000 for larger ones. But nevertheless, they're using this. The idea is that, rather than characterizing an individual by a single point, let's think of them as a distribution, get samples from it, and look at how different two distributions are, in particular, maybe a subpopulation with a condition and a subpopulation without it can be distinguished based on this. Early on a small model, they actually computed the volume of deceased patients versus typical ones and found that there's a difference. This sort of set the field over. Now, the methods for sampling, you'll see, have reached practicality to the point where the programs written by from student Ben Cousins are now fully incorporated into the systems biology toolbox, and they're doing sampling up to 10,000 dimensions. Okay, going back to the mathematics, how do we sample? I mentioned the ball walk already. Another process you might consider, which avoids one of the key difficulties of the ball walk, namely that it can get stuck. There is a probable chance that it gets stuck, either at the beginning or later. If it gets close enough to a corner, imagine a corner of a cube even, or whatever board shape you're here, this probability is exponentially small in the entire volume. So if you get that close to a corner, you're stuck. The second process, called hit and run, avoids this. What it does instead is, at a current point, it picks a random direction and a chord defined by the line through the point, and on that chord it picks a uniform random point. So there is no filtering rejection step. You figure out this chord, which you can do by asking membership queries in a binary search, and then you pick uniformly on this interval. Go there, repeat. This process is also symmetric, takes a second, you see, and goes to the uniform distribution again. But this one, unlike the ball walk, no matter how close to the boundary you start, escapes out of exponentially quickly. Okay, so here are two processes, and how do we analyze them? We're interested in the rate of convergence. This is a classical topic. A very useful tool here is the conductance, which literally is the Cheeger constant of the Markov chain. Right? It's the flow out of a subset divided by the ratio of the stationary measures of the subset and its complement, whichever is smaller. And so we can extend things to this setting, and Lovász and Šimunović proved that the distribution of the current point after t steps is bounded by its distribution, its distance originally times a factor less than 1, which depends directly on the Cheeger constant, or this conductance squared to the power of t. So in particular, after about order of 1 over conductance square steps, you will have the distance, and that's your mixing time as you go along. We have to be a little bit careful about how we measure this initial distance of the start to the end. We can't use total variation distance, but we can use, for example, the chi-square distance, and that decreases. Okay, how is this conductance going to be bounded? So now the challenge becomes to bound this conductance. How do we bound this conductance? We look at a subset, we're asking what's the escape probability, and we need to show that it's large. The probability of transitioning out of this subset is large given that you're in the subset. This takes 2 steps. The first step is purely geometric. It says that if you have 2 points that are close, then their one-step distributions where you could go after 1 step will have significant overlap. I have these 2 points, and I consider where can they go after 1 step. So if it's a ball walk, maybe that's the one-step distribution for this, and that's the one-step distribution for this. And we would like to show that these the region of overlap in these one-step distributions is going to be large. The second one is just isoperimetry, that large subsets have large boundaries. This is exactly the Cheeger constant of the stationary distribution. Putting these together, we get this theorem that I mentioned earlier, that the mixing time of the ball walk from a warm start is n squared over Cheeger constant squared. And you only need to understand the Cheeger constant of the stationary distribution. Now I want to mention a couple of other algorithmic problems to round off this first talk. Optimization is a fundamental problem in algorithms. Again, you have a function and an error parameter, and you'd like to say find the maximum but up to error epsilon. In linear programming, convex programming are special cases. So here's a simple way to do this using sampling. Sampling will come in a second. What you do is you have your subset try to ask about the center of gravity. If the center of gravity gives you some value, now restrict your set to be a half space containing the center of gravity with the higher objective value and repeat. So it's a very simple procedure that says let's just continuously query the center of gravity as the function of the remaining set. And this works nicely in a sense, namely the volume of the surviving set drops by a constant factor, no higher than 1 minus 1 over e of what you started with, because the distribution is log concave. And so the total number of queries you would have to make is only linear in the dimension, because the original volume is capital R to the n, the final volume is at least small r to the n, and so you have logarithm in that as the number of queries. The trouble, though, is that finding the centroid itself is a computationally intractable problem. It's what's called Sharpie hard. If you could solve it, you could count the number of solutions to a 3-sat formula or a k-sat formula and so on, things for which we have no idea how to do. Instead of trying to do this with sampling, we replace this with directly with centroid. We just use an average of random samples. So instead of querying the centroid, which we don't know how to compute, query the average of random samples. And this already gives you something almost as good, if you use m random samples in each step, then the volume of any half space containing this average of random samples in expectation is at least 1 over e minus square root n over m. So, in particular, if m is say 10 times the dimension, you still get this constant factor drop. And so, sampling allows you to realize this, this bound on the number of calls, which is in fact the best possible for any algorithm. You have to spend linear in the dimension and logarithm in these parameters. The ellipsoid algorithm, which was the original classical way to do this, takes n squared calls, n squared times log r order, in case you have measured. Okay. There is a different algorithm that sampling suggests. It's also conceptually very simple. Why worry about computing these averages? You keep your distribution. Let's say you start uniform. You know the objective direction, so start biasing it more and more towards the objective, so that eventually it's concentrated near the objective. So this is sometimes called simulated annealing. And so one particular sequence of distributions you could consider is exponential in the objective value. Here I've taken the objective function to be linear, just as an example. The expectation from an objective with a high enough coefficient will be close to the best possible, just because it's concentrating exponentially there, and the distribution is log concave at every step. So in particular, if we set that parameter Ti to be n over epsilon, you get within epsilon of the best possible just by taking the expectation. The last one I want to spend some time on is volume computation. And in this problem, in some sense the most basic of these problems, you've given this convex body, let's say, and you want to compute its volume or estimate its volume to within relative error epsilon. Okay. This is just remind you, we only have this oracle setting to access the body, and this this is a difficult problem. Result of allocation improved by Baran and Furedi says that if you had any deterministic algorithm that answers this problem, computes the volume, by asking n to the power of a oracle calls, think of a as 100, say n to the 100 oracle calls, then and it gives you two numbers a and b, so that the volume is between a and b. So that's what the algorithm does. Then there exists some body for which the ratio of these two numbers is essentially n over log n to the n. C is a fixed constant, 10. N over a log n to the n. So no matter, so if you want, let's say a factor 2 approximation, you have to spend n to the n time before you can get it. You have to make so many queries. It's just unavoidable for any algorithm. It's a purely information theoretic lower bound. Indeed, in fact, the situation is even worse. Even if you wanted an exponential in n approximation, you need exponential in n calls. That's a refinement of that statement. So this was all in this oracle model where you're just saying in or out. Even if you had an explicit polytope, computing the volume is sharply hard, right? But doing it exactly. So given the situation, what can we hope for? Well, we use randomness, of course, because those theorems were for deterministic algorithms. And now suddenly the situation is totally different. You can get 1 plus epsilon relative error for any epsilon in time that's polynomial, fixed polynomial in the dimension 1 over epsilon and log 1 over delta. That's the failure probability. It's a randomized algorithm, there's a chance it fails, but that failure probability goes to 0 very quickly. It's log 1 over delta. But in terms of whatever accuracy you want and a dimension, it's polynomial. This can be extended to estimating the integral of any Lipschitz log concave function. That was quickly done. The original paper is Dyer, Fries, and Cunnan, and then Applegate and Cunnan did this. And the current complexity is that the integration of any log concave function, no restrictions, can be done in n to the 4 steps, n to the 4 calls. That's the state of the art. There has been the progress on this problem is notable, not so much just because the power of the n is decreasing, but because at every step there have been very interesting techniques introduced, not just for better analysis of the algorithms, but but to analyze Markov chains, to understand geometric questions of independent interest, and so on. The last result here is not for all bodies, but for well-rounded bodies, by which we mean that the expected square distance is order of n. And for that case, it's actually just n cubed. Okay, so now that you've seen this, you could ask, does it actually work? And as I mentioned, in fact, it does. And if you're interested, you can download the program on MATLAB. It's freely available, and run it on whatever dimension body you want. It gives you instructions for how to run it. I would show a demo, but I think I'll use the remaining few minutes to. And yeah, you can go in higher dimension and so on. What I'll try to do in the remaining, how long should I go for?
You have like 2 minutes.
2 minutes, okay. Is try to sketch, these are volume algorithms, and maybe we won't have time to go over them in detail, but the point is that the computation of volume can be reduced to sampling. If you're able to sample log concave distribution, you can compute the volume. The original algorithm does it by a sequence of bodies. The current best algorithm does it by a sequence of log concave distributions. And you can think of this as taking a Gaussian density and flattening it out. Now, the fastest one, which I just mentioned, uses the KLS conjecture crucially in the algorithm. Because, well, how can we use the conjecture? Well, the conjecture is actually true for functions of the following form. If you have any Gaussian which multiplies a log concave function, for such functions, the Cheeger constant is at least 1 over the standard deviation of the Gaussian. So whatever it would be for the Gaussian is the Cheeger constant of Gaussian times any log concave. So in particular, sampling those is fast. So you don't need the full conjecture. And that lets you get a faster sampling algorithm, and as a result, a faster volume algorithm. And so I want to conclude by just mentioning a couple of remarks about the sampling problem. This was the problem, and we considered the oracle setting mostly, but you could also talk about the polytope setting, and that will also be interesting. We'll see in the next talk. Why do we want to talk about the sampling problem? It seems to lie at the heart of optimization. It helps us understand computation itself, what makes things easier and harder. It lets you solve these fundamental problems, volume, gravity, covariance, estimating the covariance, for example. It's just by picking a random sample. It lets you do things like robust optimization and online optimization. And maybe most of all, it's a window to learn more about convex sets. There is a folklore in algorithms that a problem is easy if it can be written as a convex problem. I mean, that's certainly true. But the question is, are all easy problems essentially convex? That's a rough statement. But here is a picture that might suggest the case. So if that's complexity, then here are problems. The first one is just solving linear systems, linear programming, convex programming, and sampling. And these are the current bounds. If I take m equals order n for simplicity, you can solve linear systems in the same time as matrix multiplication. That's the current state of the art. But for all we know, it should be quadratic. It should be easier than matrix multiplication. We can solve linear programs, that's a linear system. Linear programs are currently in n to the 2.5. Convex programs, explicit ones n cubed, and sampling in n to the 6, and that's the state of the art. It's n to the 6 because it was n to the 4 oracle calls, but each call is a membership test, which takes another n squared. So one thing you might hope for is maybe all of these can be done in n squared. And so the easiest way to do this is just solve the sampling problem in n squared. Okay, so here we are. I will come back in a few minutes. Thanks.
Thank you.